So, good morning. Welcome to Krishna's class. Continue with our explorations of measurable functions. It's a natural question to ask whether composition of measurable functions are measurable. That is, the measurable class of functions is this set closed under composition. Let us work on some example to get a feeling, because you know that you'll have to expect a lot of surprises, because we have got it's all centered around the fact that there are non-measurable sets. Okay, so let us start with an example. So let phi be the Cantor-Lebesgue function on interval 0, 1. Let psi x, this we have discussed earlier, psi x plus x is a map from zero to, this is 1 to 1 on to further it is continuous. All these facts we have discussed in detail. In fact, we have proved. So it's just recalling the things for the sake of what you call completeness of this lecture. Now, what one does is this following. See, this is a map. This is a map from 0, 1 to 0, 2. So it's something like this. It's just monotonically increasing. Something. Now what we do is, when a strict monotone function, it's 1 to 1 and on to, and therefore the inverse exists from 0 to 0, 1, which is also a continuous function. Now what one does is extend psi as a continuous, strictly monotone, strictly increasing function from R to which is on to. Then you see it's a 1 to 1 on to function from R to R. Okay. So something whatever be, even a straight line in something like this. So that's what is required. Okay, we shall not bother about what that extension is, but the extension has the properties that it is a continuous extension, it is strictly increasing, therefore we call this function as such. We shall denote this extension by psi itself. Therefore, what you have is this psi continuous bijection strictly increasing and has the property that psi restricted to 0, 1, this is equal to phi x plus, and psi restricted and with all these properties. Now we have shown that the Cantor set C a measurable subset with measure 0. Whenever I just use measurable, it is Lebesgue measurable. That is what it is. So we are discussing only Lebesgue measurable. Now psi of C is contained in 0, 2. It's clear. Okay. And then what more you have? You have measure of C equal to 0, measure of this is the crucial point. It is not the image of C under psi is not a zero measure C. It's measurable. Psi C is measurable, but it's with measure 1, which is not equal to 0. Okay. So we know now we are going to use the crucial results that we have seen earlier. Recall that all subsets of measurable sets with 0 measure are measurable. This is important. With zero measure are measurable. And with obviously with zero measure. However, every measurable set with positive measure has a subset which is not measured. This example uses these facts. That is, all subsets of measurable sets with measure 0 are measurable, and with measure 0 obviously. But if you take a non-zero subset of R, which is Lebesgue measurable, then it has some subset which is not. Okay. So this is the important thing. Positive measure. This is the fact that we are going. So what does it mean? So we are talking about the function psi from R. Now you take a subset. See, psi is a bijection and is continuous. So what happens? See, what you can do is to take, so there exists, see, there exists a subset A C. It's a part of you can test it such that psi of A, which is contained in psi of C, is contained in psi C, and psi C has measure not equal to 0. Okay, and psi of A is not. Now this is simple because you take in psi C a subset, you know that there exists such a subset, and then use the fact that psi is 1 to and on to, you just pull it back, and that pull back called A, which is a part of 0, 1 from the structure of psi. Okay. So that we call A, and therefore the set, the non-measurable set that we started with in 0, 2 is non-measurable. So this is what you have. You have from take psi. Now what you do is choose a set S. What do you call some set be contained in 0. Now be not measurable. Because psi of C, psi maps C to into 0, 2, and psi C measure of not equal to 0, so there exists a D. Now define A to be equal to psi inverse of, so that B is the non-measurable set, which is the image of A. But A is measurable. So A is measurable. Whereas psi of A is not measurable. So this fact we have used earlier. What we do is, so let me use Venn diagram. Probably have a visual picture of what's going on. Okay. So we use Venn diagram, but this is not interval that I'm drawing, but so this is the interval. This is R. This is the interval 0. Psi now what you have is C is a part of it. So psi C is this. This has measured 0, not equal to 0. Therefore, you have a subset A of C whose image is psi of A. Psi of A is Not A is this is the picture. This is the Venn diagram that clarifies the whatever we have. Now what one does is this. Let characteristic function now that is so chi A is defined in the whole space. So we have now two functions. Psi is there, chi A is there. Okay. Now clearly you have chi A is a measurable. That's very easy to check. So we define, this is the crucial definition, f from R to R by f equal to chi A composition inverse. See, psi inverse maps R to R and A is a part of R, therefore this is well defined. There is no problem about that at all. Now what one does is, so it's a map from R to R. Now what we do is, we choose an open interval simple. It's an open interval in R which you call I, such that I does not contain, I contains 1 but does not contain 3. Now choose an open interval R containing 1 but not containing 0. The crucial choice. We'll designate this open interval by I. So I this is this. Now let us try to pull this back with F. What about the F inverse of I? F inverse of I is all those X in R whose image under F is in I. Okay. Therefore, this is actually of I. Sorry, inverse of this. That's equal to, see, whenever I write psi inverse, I mean this is okay. But whenever I write chi A inverse, it is the inverse image that I am talking about. It's not, chi A is not a one-to-one onto function. So this is equal to psi composition now what happens here? Okay. So you see that chi inverse of A maps the point 1 to A. Okay. But all others, we don't know anything about it because 0 is not included. Therefore, this is equal to psi of which is equal to psi of. Therefore, what you have said is that psi A is not measurable. So look at this function that we have defined. These are two measurable functions. Okay. See, psi inverse is also measurable. Psi is one-to-one onto, or psi inverse is also measurable. So it's a composition of two measurable functions. But what happens is that you can find an open interval, okay, whose pullback is going to be psi A, but psi A is not measurable. Therefore, what you infer is that F is not measurable. That is, there exists measurable functions when composed may non-measurable. That means the collection of all measurable functions on R is not necessarily closed under the It's not. It's too much to ask for. Okay. All this, as you know, comes from the fascinating property of existence of non-measurable functions. Therefore, what next? Suppose we strengthen some of these properties. You take two measurable functions, but strengthen the properties beyond measurability, more than measurable. At least one function you assume is something more than measurable. It's measurable already. It's some extra punch. So let us see that. So what one can prove is this. Before that, let G be a measurable real valued on E R and F a continuous real valued function then F composition G. So we strengthened the condition on F from measurability to continuity. You know that all continuous functions are measurable, but not vice versa. Okay? So we strengthen the condition. So if you strengthen this condition, then you see that F composition G is a measurable function, where F is the continuous function, E is the measurable function. So this is the scenario that you have. You once again fall back on the Venn diagram. This is R, and you have E is a measurable subset of R. Then you have, this is a copy of R. There is another copy of R. What you have is G is measurable function, therefore it's into this, and F is from R to R, which is continuous. Now you can write F composition G. So F composition G is a map from that is well defined. Okay, right? So what we assert is that f composition G is a measurable function where this is continuous, whereas this is measurable. This is the situation. So we will just proof is very simple. So H is from now you see that H is measurable if and only if the inverse image of every open set so we make use of this theorem. Of this theorem we have proved earlier. It's interesting because the Lebesgue measure has been constructed in such a way that all continuous functions all open subsets are Lebesgue. It's a refinement of the Borel classification, the sigma algebra. It's a refinement of Borel classification, which is the minimal, what do you call, measurable sets containing all open sets. But we have shown that it's quite powerful this result is quite powerful, which we have seen. Therefore, let now what we do is we work on this F composition G, that is H inverse of which is equal to G inverse and since F is continuous, F inverse O is what? Hence, now G is measurable. G inverse of is measurable, which implies H inverse of measurable which is measurable. That proves it. That is F composition G is measurable. Now this is a very useful result. Okay. The application is there is enormous possibility of applications. Now we'll just record some of them for on E. Mod G is measurable. Further, mod G to the power P is measurable on E for every P positive. Now this is quite interesting. I mean, it's very simple. You can just pull it out from this theorem by making an appropriate choice of the continuous solution. So what we do is we define if you take P equal to 1, result in the first state. Okay. Then now you see that we take F composition. F composition G is what is F of Gx? Now this is equal to mod Gx. And this therefore we know that H is measurable. The first statement is when P equal to. So that proves it. It's a nice result. Now we go beyond this. Now later it will be clear why we do all this. So let me just work. Suppose you have a finite collection of functions defined on. Now you can define two functions, say just n functions. You can define a new function by taking the maximum of all these finitely many functions at each point. That defines a new function. Similarly, by taking the minimum, you can take another new function. Now the question that you ask is, suppose we know that the functions that you have chosen are measurable. Are these functions obtained by taking the maximum and the minimum are measurable? So let us put this straight away. Right? Okay. So this completes the proof. Let finite family of measurable functions okay. With common domain. Now define G to be and H should define minimum of that means what you are doing is G at X is taken as the maximum of the n numbers f1x, f2x, etc. and so on. Similarly for so that defines a new function. So these are two new functions defined. The question is, are these functions? This is the question. What we are up to is to investigate this question. Okay. So now we do some exploration. So we build up. Just examine what happens with two functions instead of 10 functions. And see how possibly you can investigate this. So we shall explore this question choosing two functions. So how do we do that? Okay, let's choose two functions. Some specific example we are taking and from which we are trying to work out the. Okay, or simple. Take the interval as now we take both f positive g f1 positive and we draw the picture of these two functions. Take the graph of these two functions. Yeah. So what you have is this. Suppose this is the function. Okay. Just take the function f. Now what is maximum of f1 f2? Maximum of f1 f2 is this one. Okay. This further this one and further this one. This is maximum of. So this is which you call G. Okay. Therefore, what we want to investigate is whether G is measurable or not. We use the standard criteria. For any arbitrary C, we try to work out this. Choose an arbitrary C and then look at this Z to infinity, pull back of this under G. How to get the pullback of this? This is the pull. These two sets is the pullback of this. This is G inverse of so this is the portion. G inverse of. Now you want to see how do you get this in terms of F1 and F2. What is F1 inverse of C infinity? F1 inverse of C infinity is, what is this? This is your F1. F1 inverse of C infinity is this. Okay. And F2 inverse of C infinity is what? F2 inverse of C infinity is F2 inverse of C infinity. So this is your this is infinity. Now what can you say about this? You observe that G inverse of C infinity is infinity. This is it. Now you see that each of this is measurable because F1 is measurable, F2 is measurable, therefore each of this is measurable, therefore their union is. Now this is the sort of argument. Therefore, how do we generalize this for some n sets? Sorry, n functions. You expect the union of F1 inverse of C infinity, F2 inverse of C infinity, etc. Fn inverse of C infinity equal to G inverse of C. Okay. Now, what happens in the case of uh, what you call the minimum? Okay, let us explore that also. Then we can just finish in one line. Now you see that this is okay. Therefore, what we are calling is the minimum. The minimum of this is F1 color device. This is F1. This is. What about the minimum? The minimum is this. This is the minimum. Now you take for arbitrary C, we'll work it out. So C for now this is C infinity. Okay. This is C. Choose the pullback of it. Pullback is this and so you have pullback will this part this is H inverse of this. That is H inverse of C. Now how does that come? So what is F1 inverse of C infinity? F1 inverse of C infinity is this one. F1 inverse of C infinity is this and this portion goes from here This is what about F2 inverse of C infinity? F2 inverse of C infinity is this portion. What you call, yeah, this one, that is this portion. Then you have this portion. So this is F2 inverse of. Now you observe that, see the white, subset and the violet subset. Sorry, the violet subset is essentially the intersection of the white subset and the brown subset. Okay. So you take the intersection, you see that this portion is there, and then of course this portion is there, this portion is there. So you observe that H inverse of the section C infinity. Now this is again, once again, these two are measurable because F1 and F2 are measurable. Therefore, their intersection is measurable. Therefore, H inverse of C infinity is measurable for any arbitrary choice of C. Therefore, you see that G and H are measurable. That is the sort of argument. Now just do it for the general case. That's all. So let us write down the theorem. But of course, this is not no proof. This is just a sort of pictorial verification, which is not a proof in mathematics. So you have to show that this is, see, whenever you want to show that a set is equal to another set, you have to show that the condition that if you want to show that two sets A and B are equal, you show that A is contained in B, B contained in A. So here you have a set here, you have another set here, described in two different ways. Now you have to show that every element here is in here, every element here is in. That's all. So that's how you have to prove it. This is no proof. What I have shown is just a sort of investigation which gives some insight into how one would approach to prove this result. How you really speculate this result. That's also. So let us write down the theorem now. For a finite family of measurable functions, with a common domain, define G So that's the theorem. Now the proof is very simple. Similarly, now you see that here it is a finite union, here it is a finite intersection. These are measurable sets, therefore it is measurable. Measurable. Being the union and intersection sets. Being the intersection finite union and finite intersection of that's fine. But that's just a not merely a curiosity, but it's a very useful concept, as we shall see as application of this. Okay. So we make some remarks, or we can write for right. Now Then of course you can, it's also odd f. This also you get. If f is measurable, minus f. So this is a simple application of these statements follow immediately by applying the above theorem. The measurable functions f 0 x. So that is simple, straightforward. Okay, but this result is performed. Says that if f is measurable, mod f is measurable, and if both f plus and f minus are measurable, all these are nice results. Okay, and very useful results. So I think that answers all the questions regarding measurable functions, and we shall stop the stage. Thank you very much. So